Hello everyone, this is part 7 on the compression steel. Let's solve more problems. This is example 10.3 and the problem reads, an unbraced hinge at base column, as shown in this figure below here, is fabricated from grade 50 steel. Determine the limited state that will control the design of the column. Let me grab my pen. And let's read the problem statement carefully. It says unbraced hinged at base column. So that tells me if it's an unbraced hinge at base column. So we are at the lower story of the building. That's one thing to remember. And here it's asking you just to identify the limited state. If you're confused with the limit state, you need to watch my previous lectures about the limited state. But we want to identify the limited state, the type of limit state that will control the design. So to start with, we have to find the width over the thickness, right? So the width is 10 over the thickness, which is 0.25. And this gives me 40. Now, if you go to table 10.1, remember here we have a box, in a box or tubing scenario, that's what we should check against, 1.4 times the radical and so on and so forth. So the value here, plug in chug, it's 33.72. This value is less than the width, the ratio of the width over the thickness, which means the column is slender, and because it's a slender, we have to use the reduction factor. How do we find the reduction factor? Because it's not given, right? We have to find it. So first, let's work on the moment of inertia. The moment of inertia I equals the I for the outside, the perimeter, minus the inside. Why we are doing this? Because this is a built section. It's not a section that a rigid solid comes together. It's a built-up section. So the moment of inertia is something we have to find it. We have to calculate it. So then the moment of inertia is the outer of the moment of inertia minus the inner. Now, if you remember, I'm sure you've taken this in a math class before or something. The moment of inertia for a square is I, also in the statics, I think we've taken it. It's B times H, excuse me. Let me erase this because this should be H cubed over 12. Width times the height cubed over 12. So the outer is 1 over 12, right, times 10, because it's a box or squared, so all the sides are equal. It's 10 times 10 cubed minus 12. Now we are working on the inside. 9.5 times 9.5 cubed, because it's 0.25, right? Two sides, so it's 0.5. 10 minus 0.5 is 9.5, and that goes for the two sides. So our moment of inertia for this built-up section is 154.58 inch to the power of 4. What is the gross area? The gross area is 10 by 10 minus 9.5 by 9.5, right? The outer minus the inner, and this gives me 9.75 inch squared. Why did we have to find the moment of inertia and the gross area? Because the radius of gyration is under the radical moment of inertia divided by area. So now we found the radius of gyration. Again, if you go back to my lectures and verify on this, If you're working on a lower story column, then your K is always 2. So then you have, here you have it. We found K, the radius of gyration. We found R, radius of gyration. We find K, the effective length factor, and we already have the length. So then to find the slenderness ratio is a 2 plug and check, right? 20 conversion to inches by 12 over 3.98, and this gives me 120.6. Now from table 10.2, you find this value to check against it to be able to identify if the column is elastic or inelastic. So our value here, which is 120, is larger than this value, which means the column is elastic. And because of that, the mode of the mode of failure that is controlling, or the limited state, excuse me, that controlling is the lowest of the following: elastic flexural buckling with the slender reduction factors, or torsional buckling with the slender reduction factors. And that's it. The problem, that's all I needed.